All right, we're going to be taking a look here at linear independence. We've already done a video on this. We're just going to continue. This is part two. Just going through lots of examples of questions working on the idea of linear independence and linear dependence. Let's take a look at our first example here. So in this question here, it says they want you to find all the values of t such that the set is linearly independent. So in this case here, we have a set of three vectors. We want to go ahead and see whether these are linearly independent, what values of t make them linearly independent, if any at all. So first thing we're going to do is put this in a matrix here, right? Again, we're writing these vectors column-wise. And now that we've written the vectors column-wise, we want to go ahead and I want to make these entries 0. So I'm going to take row 2 minus t row 1. And here I'm going to take row 3 minus row 1. And continuing on here, I'm going to end up getting 0. This will be 1 minus t squared. This will be 1 minus t. And this will be 0, 1 minus t, and t minus 1. So right away, as I look at this, I can make the observation that this row here, if I let, right here in this row, if I were to let t be 1 here, that would generate a 0 row for me, making this set linearly dependent. So what we're going to do here is we're going to assume, in this case, that t is not equal to 1. And we're going to continue with this matrix in this manner. And the reason I'm going to do that is I can push this further if I know that t is not equal to 1. So we already know if t is 1, the set's dependent. I want to see what happens when t is not equal to 1. Are there any other conditions that give dependency here? So by letting t not equal 1, what I can do is I can go ahead and I can divide across this row by 1 minus t. Because if t is not equal to 1, then 1 minus t is not equal to 0. So we're not dividing across by 0. So I'm going to take this entry here, the 1 minus t squared. That'll break up into 1 minus t times 1 plus t. So that when I divide across by 1 minus t, again, doing that on the second equation here, you're just going to be left with a 1 plus t in this spot here. And then the next entry, we're going to be left with a 1. Again, divided across by 1 minus t. And doing that again on the third row, I'm going to get 0, 1. And this will end up being negative 1 here because you can take the t minus 1, you can factor out the minus sign. So I can rewrite the t minus 1 as this. So when I divide across this equation by 1 minus t, you can see that'll be 1. And this will end up being a negative 1 doing this substitution. All right, so now that I'm here, I want to push this further again. So I want to see if I can make this entry a 0. So what I'm going to do is I'm going to multiply row 3 by 1 plus t, row 3, and I'm going to subtract row 2 from that. So the first row is unchanged. The second row is also unchanged. And the third row becomes 0, 0. And then this ends up being negative 1 minus t minus 1. And putting this all together here, we get 1 t, 1, 0, 1 plus t, 1, 0, 0. And this ends up being, I end up getting here negative 2 minus t, in which case you can multiply across by negative 2. And I end up getting 0, 0, t plus 2. Just clean up, multiply across by a minus sign. So now again, I'm under the assumption that t is not equal to 1. So if t is not equal to 1, what's another way that we can get dependency here, and that happens right here again, you can make the observation here, if t is equal to negative 2, I end up getting 0, 0, 0 in that third row again. Again, you get linear dependence in that situation. So therefore, if t is not equal to 1, we can get ourselves to here. And if we still want to have independence, I have to add another condition that, and on top of it, t cannot equal -2. If t is not equal to 1 and t is not equal to -2, then we're in a situation that we have ourselves a linearly independent set. And these two conditions, any one of these two conditions will generate ourselves a linear dependent set. All right, let's take a look at another problem. In the next problem here, they give us the set of all polynomials having degree at most 3, and they want us to determine whether the following set is linearly independent. They give us this sort of set here, set of this is a subset of our set P3 here, and they're saying if it's dependent, find a non-trivial dependence relation. If it's independent, justify. So if we take a look at this question here, the first observation or thing to remember is a basis for this set is 1x, x squared, and x cubed. And what I mean by that is any element coming out of P3, i.e. a polynomial of degree at most 3, can be written as a linear combination of these. And this is the smallest set that does the trick. If you haven't seen that, we'll examine this further in the basis videos, going through basis. But at any rate, I want to be able to write this in terms of some basis. So this set S, I'm going to write in terms of my basis B. And if I do that in matrix notation, you can see this is 1 times the first, 1 times the second, and 1 times the third, and then 0 times this entry. So my first entry is going to be 1, 1, 1, 0. Again, the next entry here, I have no constant term. I have a 1 in front of my x basis vector. There is no x squared here, so it must be 0. And the x cubed there must be 1. Then I move on to this one here. This ended up being 1, 2, 0, 1. And then this right here will be 2, 0, 1, 1. So now I've rewritten my set S in terms of its basis vectors here. And I want to go ahead and see whether it's linearly independent, right? If it is, then this set S is in fact linearly independent. If not, if it's dependent, I can find the combination that it works with here. So I'm going to go ahead and make these entries 0. So I'll take row 2 minus row 1, row 3 minus row 1. When I do that, I get 0, 1, 1, -2, 0, 0, -1, -1, and then 0, 1, 1, 1. And continuing on here, I'm going to make this entry 0. So I'm going to take row 4 minus row 2. While I'm there, I'm going to go ahead and just multiply row 3 by -1. So I can make these positive. Oops, sorry, let's put that in black. Make these positive. And then subtracting row 4 minus row 2, I get 0, 0, 0, 3. All right, continuing this on here, I want to go ahead and make this entry 0. So to do that, I'm going to go ahead and take row 1 minus row 3, and then row 2 minus row 3, in which case I end up getting 1, 0, 0, 1, 0, 1, 0, minus 3, 0, 0, 1, 1, 0, 0, 0. For the last one here, I'm just going to multiply by a third just to clean it up. So I get a 1. All right, to finish this off here, I'm going to go ahead and make these entries here. I'm going to go ahead and do row 1 minus row 4, row 2 minus, or plus, row 2 plus 3 times row 4, and lastly row 3 minus row 4. I'll use that as my anchor. All right, performing these operations here, I've got row 1 minus row 4. It's going to give me 1, 0, 0, 0. Then row 2 plus 3 times row 4. It's going to give me 0, 1, 0, 0. Then I've got row 3 minus row 4 is going to give me 0, 0, 1, 0. And lastly, the last row is unchanged. We get exactly the identity matrix. So this set here is linearly independent. So we already have, this set is already linearly independent, and illustrated here by row reducing, writing this in terms of its basis vectors, then writing my matrix, row reducing, getting the identity. So we know that this is in fact linearly independent. All right, let's take a look at another example. All right, in our next problem here, they want us to prove that the set UV is linearly dependent, and that is equivalent, so if and only if U is a scalar multiple of V. So this is an if and only if proof. This is bidirectional. We have to show it both ways. So I have to show that if this is the case, it yields this result. And likewise, if this is the case, it will yield this result. So let's go ahead and try to prove this proof one way. I'll go ahead and assume that UV is linearly dependent. And I want to prove that U is a scalar multiple of V. Well, if UV is linearly dependent, therefore exists coefficients C1 and C2, at least one of them not equal to 0, such that C1U plus C2V is equal to 0. But therefore, that implies that C1U is equal to negative C2V, which means that U is equal to negative C2 over C1V. And therefore, that means right away that U is a scalar multiple of V. So I went ahead here and I've assumed that the set's linearly dependent, so there must exist coefficients, non-zero coefficients, whose sum come out to be 0. That's the definition of linear dependent. But by that, you can isolate for the vector U and write it as a scalar multiple of vector V. So therefore, right away, we know that U is a scalar multiple of vector V. Okay, let's try the other way now. So I'm going to go ahead and I'm going to assume that U is a scalar multiple of V. And I want to show the set must be dependent. Well, if U is a scalar multiple of V, therefore I know there exists a some coefficient C such that U is equal to C times V. But therefore, if I bring this to one side, I end up having that U minus CV is equal to 0. If you want to adjust this, I can K equal negative C, and therefore I have U plus KV is 0, where at least K is not equal to 0. So now what I've done is I've found a situation where a combination of vectors is equal to 0, but their coefficients are non-zero, and therefore this is in fact the proof showing that this is linearly dependent set U and V, right? Because the set would be linearly independent, i.e. its negation, if the only way you could get the combination of the vectors to come out to be 0 is if the coefficients themselves are 0. And I've now shown that I can do it. I can get this combination to come out to be 0 where these are non-zero coefficients right here, right? So U is a scalar multiple of V. Here, implicitly here, this under the assumption here that C is not equal to 0, right? Else that would mean U and V are the 0 vectors, right? So not considering that case. All right, that'll end this video going through linear independence. Take a look at there'll be a part 3 here going through some more examples of linear independence as well as other topics in linear algebra. Thank you.